kicking myself for getting that wrong. Ugh, embarrassing. Okay, well, I will put a little box around this as a memorial for my mathematician license and erase the rest of this. And, yeah. That's going to kill me. Okay, stop thinking about this. Okay, so let's say we're running Gram-Schmidt, right? And we want our K of search direction. Right? How are we going to do it? Well, we're going to start with the previous residual, just like I said. Yeah? I guess I was doing K plus 1, but now I'm going to do K and K minus 1, just to induce more confusion. Right, and now I'm going to subtract off my projection onto all the previous guys. Right? And the previous guys are already A-orthogonal, right? Which is nice for projection, if you remember our lectures on QR. Yeah? In particular, what we're going to do is we're going to sum for all I less than K, right? And the projection onto VI, right? And what does the projection formula look like? Well, if you recall, it looks like the dot product of the thing that you're projecting and the current vector divided by the norm of that vector. And in fact, you can check on your homework that this still works for the A inner product. And so in particular, what you're going to get is that this is, remember we're projecting this guy, so it's RK minus 1, dot product with VI. And this is now the A inner product instead of the dot product. Is the only change from Gram-Schmidt. VI inner product VI. Yeah. But what did we just almost prove? We just almost proved that every term in the sum except the last one is 0 already. Yeah? So in particular, we get this amazing, exciting, super cool formula which says that this in fact is simply equal to this guy, RK minus 1, VK minus 1, the A inner product divided by, this is, I don't like writing all this stuff down. Okay. How much time does this formula take to evaluate? Well, there are K terms in this sum. Yeah, K minus 1. How many, well, okay, it starts to do. How many terms are in this sum? 1. Right? So what did I just do? I gave you a nice strategy, a nice recursive strategy for generating A orthogonal directions, or otherwise known as conjugate directions, just one after the next. And I don't even have to store all my previous directions, right? When I do Gram-Schmidt, I would have to store the whole list of directions I've seen so far and project them all out. But in fact, I get lucky here, and I only have to store the last one I saw. And all the rest of them are already orthogonal because of this nice interaction between my search directions and my residual. This is cool, right? What it means is that the 20th iteration of conjugate gradients doesn't cost us any more than the first, which is not something we would have predicted from the Gram-Schmidt algorithm. Yeah? Okay, so hopefully you guys are somewhat following despite the little mistake. Thankfully this is a proof mistake rather than something critical. Right, so what we have so far is a way to generate A conjugate directions and a very good understanding that if we have a bunch of conjugate directions, we have a very nice algorithm for finding roots. And let's write that algorithm down. Basically, we return to our old guy here. Okay, and now let's update our formulas. Where did my eraser go? Let me see where I put it down. Right. Now we have a way to fill in step 1, and the rest of the algorithm, which we already agreed, because nobody's asking any questions, is correct and beautifully derived. It just remains the same. Yeah? So now we just copy our formula from before, right? Where you're going to take, remember that if we were doing gradient descent, all I would do is leave this the way it is here. Yeah? I would just take my search direction to be the residual, because that's the gradient, well, minus the gradient. But now what I'm going to say is, in fact, no, what I should do is A, project out my previous search direction. Hopefully I'll get these right. Yes! Yeah. So what is the difference between gradient descent and conjugate gradients? It's this. That's it. Everything else is the same. Yeah? So if you can implement gradient descent, you can implement CG. Yeah? And the nice thing is, what do we know about CG? It does strictly better than gradient descent in all cases. Right? That's what we prove, because it is always, well, I guess strictly isn't true, but it never does worse than gradient descent, and oftentimes it does better, because it is always optimal in the subspace of search directions that you've looked in so far. Yeah? By the way, if you could somehow generate search directions that are orthogonal in X space, you could also have this property, but that's not as easy. Right? The nice thing that happens in conjugate gradients is that in order to develop a bunch of conjugate search directions, you only have to project out one guy instead of k guys, which is surprising, right? You guys should be like duly surprised right now that this should happen. It's like the only time in life when this ever happens, and it's so nice. Yeah. By the only time in life, I mean like almost any Krylov subspace method has this property, but the only one we care about is CG. Okay. So what are some properties in this? Case I haven't repeated myself enough times. Xk is optimal in the subspace spanned by the first k directions. Right? That's what I keep saying, which is that every time I add a new search direction, I'm decreasing f, and I'm doing so in the best possible way in the span of all the search directions I've had so far. This is different from gradient descent, right? Where all I can say is that my line search is optimal for the direction I just wrote down, but I don't know anything else. Yeah, does that make sense? Okay, what else do we know? Well, we know that my laptop isn't very good, and that f of xk, right, remember we had this quadratic form, is upper bounded by f of the kth iterative gradient descent, and that is just a consequence of the first statement. Right? Because the kth iterative gradient descent is also in that subspace, but we didn't prove that it's optimal. Yeah? And finally, we know that the algorithm converges in n steps because we were able to generate n conjugate directions. Very cool. Alright. So in the notes, assuming that I didn't make more critical math mistakes, I wrote conjugate gradients in the form that most people are used to, because our proof is slightly different from Shuchak and some of the other ones that you've seen. And so in fact you can do some simplifications to assorted steps here that are not particularly meaningful but a little bit easier to evaluate mathematically. So I'm going to copy those down on the board because we're going to keep sort of updating our CG algorithm during today's lecture and adding new features and bells and whistles. So in particular, right, basically the first step, I divided the search direction into two steps where I compute a constant beta, and then we just noticed that the new search direction comes from the old one with some beta in it. Yeah. So that looks like beta k is equal to rk minus 1 transpose rk minus 1 divided by rk minus 2 transpose rk minus 2. We kind of like this expression for beta because it is clear that numerically speaking, if I implement this formula, I will get a positive number. Right? The formula we had before with the projection, that might not have been the case if we were using rounding and all kinds of stuff. Right? But this is just two norms, the ratio. Yeah? And then we say, okay, and Vk is equal to Rk minus 1 plus beta k Vk minus 1. Yeah. So all I did is I just split this formula for Vk into two steps. And then also, you can get a better expression for alpha, which is Rk minus 1 transpose Rk minus 1 divided by the same denominator. I think. Yeah. Okay. Cool. And this is the standard form of the conjugate gradient algorithm. Cool? So again, what really you should keep in your head, like on your exam, I promise, I know I give hard exams, but I promise you don't need to memorize this algorithm. What you do need to know is what these 4 steps are doing. Yeah. So again, we generate a conjugate search directions, we do a line search, we update our current estimate, and we update the residual, because the residual helps us generate directions. Okay. And this is all in your notes, so I will fix this proof. Okay. So here's the thing. Now, just like gradient descent, converges, right? And we show that the ratio of f at one iterate to the next decreases, right? The same thing happens for conjugate gradients, obviously, because it's bounded above by gradient descent. And generally what this means, remember that the CG algorithm, unlike Gaussian elimination, the CG algorithm is really tuned for like gigantous matrices, right? Like you can have a billion by billion matrix and run CG on it if your matrix is very sparse, for example, right? And so what that means is that, well, if you really want the solution to AX equals B, you're going to have to run a billion steps of conjugate gradients, but that's an awful lot. So in fact, what we normally do is we notice, well, okay, so the whole point of CG is that it is moving along directions of steepest descent, right? It's just doing so in kind of a smart way. And because of that, chances are within, even by like billion by billion matrices, often within like 20 to 30 iterations, your solution is within a few decimal points of the actual one. It's quite surprising. So what do? Usually you stop CG early rather than running it for all billion steps. Yeah. And of course, one thing you have to do is decide when are you done. Yeah. A very poor implementation of CG would just say run it for 20 steps and stop, because it depends on the conditioning of your matrix and lots of other properties. Right? Unfortunately, this is the same problem that we discussed in like week 2 of this class, right? Which is that you can't actually compute the condition number of a matrix, right? So usually what we do is we say, okay, typically if our residual that we have in the kth iteration is much, much smaller than the residual we had at iteration 0, then we're pretty sure we've converged within some degree. Yeah. So this would be a typical stopping condition. Another stopping condition might be like you look at the last 5 values of x, and if x hasn't changed a whole lot, then you stop. Right? This is an engineering decision. There's not a whole lot of science there. Okay. So if you thought convergence of gradient descent was annoying to analyze, convergence of CG is strictly more annoying to analyze. And so this formula we will state without broken or unbroken proof. And basically, the convergence of CG looks like the square root of the condition number rather than the condition number itself. Yeah. So this immediately tells us that in fact CG converges much more quickly than gradient descent. In fact, this is a very rough estimate for the convergence ratio. If you look in Golub and Van Loen, for instance, right, this very advanced book on numerical methods in linear algebra, what really is going on here is that it depends on the distribution of all the eigenvalues of your matrix. Right? So what conjugate gradients really likes is if your smallest and your largest eigenvalue are in a very small band, and that all of your eigenvalues inside of that band are nicely spread out. Now why is that? You can actually draw a picture of why you might expect that to be the case, surprisingly. Because remember when we talked about level sets of our function f, we decided that when the level sets look like circles, right, then we're doing pretty well because this gradient descent strategy kind of shoots you right in the middle, right? And so somehow when all of your eigenvalues look similar, that's when you have the circular case and your gradients look very nice, right? When your eigenvalues are very different, then you have this very funky shaped function that's a little bit harder to navigate. In fact, one way to sort of evaluate the conditioning of a matrix would be to run a few iterations of CG or gradient descent and see how successful they are. Okay, but here's the next observation we're going to make, is that almost any iterative scheme you can write down for solving AX equals B. And by the way, these are only 2 of a very large class of methods. Almost any of them depends on the condition number for figuring out how fast they converge. This is a little bit different from, say, Gaussian elimination. Right? Gaussian elimination, the condition number told us how much we thought we could trust the answer, but it didn't tell you how fast our algorithm was going to run. Now, the condition number we proved last class, we stated last class, in this class, sorry, actually tells us not only how much we can trust the output of our code, but also how many iterations we have to run before we can expect convergence, right? So the condition number has a very important bearing on both the speed and quality of our code. So there's a really cute trick that we use to make conjugate gradients run a lot faster. So conjugate gradients is already a little bit faster, well, considerably faster than gradient descent, but we can actually do much better. And this is so surprising and so cool. Here's the observation. The condition number of a matrix and the condition number of some matrix P times that matrix A, those are not the same condition number. Yeah? In particular, let's say that I took P to be equal to A inverse. Right? The condition number of A times A inverse, the condition number of the identity matrix, which is 1, for almost any reasonable condition number, and the condition number of A is whatever it is, yeah? So obviously you can pre-multiply matrix by other things and change its conditioning. So a very common strategy would be to say, okay, well maybe we can guess some p that makes the conditioning of our matrix a lot better, right? And then rather than solving ax equals b, we can solve pax equals pp. Yeah? And clearly these two things are going to give us the same solution. And this strategy is called preconditioning. So the idea is, obviously we don't know A inverse, right? We're trying to solve Ax equals B. But maybe we can make some approximation of A inverse, we'll call him P, right? And then somehow, because P looks like A inverse, the conditioning number of PA is much better than that of A. And thus, conjugate gradients, or gradient descent, or whatever, will converge a lot faster. Yeah? I think this is actually a pretty reasonable trick in the scheme of things. Smart, but reasonable. Unfortunately, there are two problems with this strategy. Well, the first is, remember that so far we only have algorithms for dealing with symmetric and positive definite matrices, right? But if I pre-multiply by a guy p, then it's neither symmetric nor necessarily positive definite. Yeah, so that's not so good. And finally, and additionally, I haven't told you what p is, right? Obviously, I can't compute A inverse, so we need some kind of reasonable approximation of the inverse matrix that's going to give us better conditioning than we started with. Yeah? Okay. So to deal with the first problem, there's a ridiculously clever trick that people use. And this is called symmetrization. Okay. Eraser. There it is. Okay, I'm going to erase these two boards, I think, can go, and I'm going to leave CG up there. And I'm going to erase the memorial from my math skills, if that's fine. If I don't fix this in the next day or two, send me an essay email and I'll take care of it. Sorry, the proofs here aren't hard, I'm just bad at basics. Okay. Right, so let's say that P is symmetric and positive definite. Right. By the way, is it okay if I use SPD for symmetric positive definite today? Right? Then, by the way, this pretty obviously implies that P inverse is also symmetric positive definite. Yeah? You can check this at home if you don't believe me. And in particular, what this means is that I can write P inverse using our favorite decomposition for symmetric positive definite things, the Cholesky decomposition, right? I can write P inverse equals E times E transpose. I'm not going to use L because we kind of already used that last lecture. Yeah? So here's going to be the clever observation of today, which is that the condition number of P times A is the same as the condition number of splitting P in half and putting one half on the right-hand side of it. This is not an obvious statement, but it actually is kind of a reasonable hypothesis to make. And the reason is that basically what happened here, right? By the way, notice that if P inverse is E transpose, this means that we can write P is equal to what? E, we'll say minus T, and it means that that's E to the negative 1 transpose, times E to the minus 1, right? So what happened here, right, is this is PA, but we kind of removed one of the E's on the left and stuck it on the right. Yeah? This is actually a pretty common strategy in advanced linear algebra. Now, why should this statement be true? Let's write a proof. And actually, when you write the proof, you'll see that it's actually reasonable how somebody might have guessed this theorem. Okay? So, right. So in particular, we're going to show that we get the same eigenvalues out of both of these matrices, right? And then that's going to tell us that the conditioning is the same. Okay, so to do that, let's actually start on the right-hand side. So let's say that e to the minus 1, a to the a e to the minus transpose, right? That's our first one times some vector x equal to lambda x. Yeah? Well, we know that p is equal to e to the minus transpose, e to the minus 1. Yeah? So how could we get a p out of this? So we could multiply both sides by e to the minus transpose. No? So this implies e to the minus transpose. E to the minus 1 a e to the minus transpose x is equal to lambda e to the minus transpose x. Okay. Now, and this thing, assuming that I did it right, is this, right? So this is just p. Okay? And now I'm going to do one additional trick, which is I'm going to label this vector, e to the minus transpose, e to the minus t times x. We're going to label this guy y. Yeah? Well, and notice that y also shows up on the right-hand side. See, this is the clever trick. Right? Basically, you know, kind of like when we were talking about linear algebra, and I said, like, anytime you don't know how to do a linear algebra problem, substitute the SVD and see what happens. A common strategy in this area of math is anytime you don't know how to do something with an SVD matrix, substitute the Cholesky factorization and see what happens. And that's basically how somebody could have gotten to this proof, right? It's by substituting the Cholesky factorization for P and kind of working backward, right? Because what did we just show? We showed that P times A y is equal to lambda y, and in particular, this means that you can take any eigenfunction, or rather eigenvector of this matrix, right, this thing on the right-hand side of our proposition, and we can turn him into an eigenvector of P times A, right? And this process obviously kind of reversible. So in particular, they have the same spectrum, and in this case, since the guy on the right is symmetric and positive definite, that means that they have the same conditions. Right, because they have the same singular values. Cool? Alright, so we're going to try and keep our number of botched proofs to 1 today. I'll see if I can make that challenge. Yeah? So, how could we make use of this fact? Well, the thing on the left-hand side, we decided he's no longer symmetric and positive definite, but the guy on the right is. Yeah? Because A is symmetric, positive, definite, and you sort of pre-impose multiplying by something until you transpose. It's easy to check that that doesn't change symmetry or quasi-definiteness. Right? Certainly not symmetry, right? If I read this in reverse order and transposed everything, I get the same thing back. Okay. Right, so how could we solve this? Well, let's say that I solve this first system, right? Which you notice is nothing more than kind of what I've already written inside of our proof, right? I'm gonna solve e to the minus 1a to e to the minus ty equals e to the minus 1b, right? And then do a second solve for x. Yeah? And you can check that in fact PAX equals PB if you solve this. This is sort of similar. Remember when we did LU factorization? We factorized the matrix as LU, and then we showed that we solve in 2 steps. This is basically the same trick. Okay. So let's say that we wanted to do better conditions CG, and somebody had given us a preconditioner P, and in fact not just a preconditioner, but a Cholesky factorization of a preconditioner. It's a very unlikely situation, but maybe they did. Well, what would our CG algorithm look like? Well, okay, so all we have to do is go down our old CG algorithm, and anytime we see a matrix A, now we're going to put in this weird matrix e to the minus 1, A, e to the minus transpose. Yeah? So in fact, let's just do that. And once again, I misplaced my eraser. Okay, so where's matrix A? Let's go on a search and destroy mission. By the way, we can erase this guy for now. Here's an A, so let's put one here. So this is e to the minus 1a, e to the minus 2vk. Yeah? Hopefully I got that right. Yep. This stays the same, and here we have an a vk. So now he's going to become an e to the minus 1a, e to the minus t vk. Okay? So in fact, it only changes in 2 places. Not so bad. But here's the problem, which is that this algorithm is totally worthless, right? Because not only do we not know how to find a preconditioner yet, if we do find a preconditioner, we have to Cholesky factorize this thing, and we know that that is equally difficult to solving our initial AX equals B. But here's going to be the trick, is that we make a very clever substitution. And in particular, we're going to define RK tilde to be equal to E times RK. Yeah? We're going to define VK tilde to be equal to E to the minus T times VK. Sorry, without my notes, I would have no hope of doing this. And XK is going to be equal to E times YK. Oh. And then our other fact about life that we're going to need is this formula right here. Right? Because our goal is going to be to try and stick, like anytime that I see an e to the minus 1, I'm going to want to stick an e to the minus t next to it so that I get p. Right? Because I'm good at applying p, I'm not good at applying Cholesky factors. You see this game? So let's see what happens if I make this substitution. This is a K. Well, what happens to step 1? Well, okay. So now we want r to the k minus 1. We want the dot product, the norm of this guy, right, for r k minus 1. So we have to put an e to the minus 1 over here. Right? So in particular, this thing is equal to what? Well, beta is equal to e to the minus 1 rk tilde, transpose e to the minus 1 rk tilde, right? Because that's just another formula for rk. Divided by the same ratio for r. Oh, this should be rk minus 1. See, that is e to the minus 1 rk minus 2 tilde, transpose e minus 1 rk minus 2 tilde. Okay. Now here's something really neat that happens. Right? Now remember, the transpose of the product is a product of the transposes in reverse order. Right? This is one of our favorite formulas in this class. So in the end, you're going to get, this is rk minus 1 tilde e to the minus t times e to the minus 1 rk minus 1 tilde. And the same thing in the bottom half, right? rk minus 2 tilde e to the minus t e to the minus 1 rk minus 2. Yep. So all I did was just expand this product, right? But look what just happened. Yeah? By making the substitution, these guys, yeah, using our favorite formula here, are just equal to p. Yeah? So in fact, this whole formula for beta just looks like r tilde k minus 1 transpose p r k minus 1 tilde divided by r k minus 2 transpose p r k minus 2. Yeah? So if we make the substitutions upstairs, then we got rid of all the e's, and now we just have p's because of this this convenient factorization. Actually, because of where we started. Yeah? So now we can compute, if somehow we can compute these r tildes, then now we can compute beta. Right? In fact, this is what, beta k? Yeah. Alright, so this formula is taken care of. This formula remains the same. No, it doesn't, it's a line. Okay. So what ends up happening now? Let's do maybe one more example of this, and then hopefully you can agree with me that this trick is going to apply to all these lines. Right? So in fact, this isn't even a 2, this is like a 1.5, yeah? Okay, so we have that vk is equal to rk minus 1, beta k, and all this stuff. Yeah? And now we have a way to compute beta, so he's fair game. Okay, so what is vk equal to? Well, that's just e transpose times vk tilde. Yeah? And on the right-hand side, we'll look here. What is rk minus 1? Well, we just go into our dictionary here. This is going to be e to the minus 1 rk tilde. Yeah, and then finally we have plus beta k vk minus 1. And vk minus 1 we already decided is the same as e transpose vk minus 1 tilde. Yeah. So now, if I multiply both sides by e transpose inverse, right, so I just multiply by the inverse of this guy on the left, then what do I get? I get that vk tilde, well, so this is e to the minus t times e to the minus 1, our favorite formula yet again, tilde, plus beta k, and now this is the inverse of that. So yet again, my e's going. Yeah? So in fact, I think I can probably, hopefully you guys trust me, that the remaining steps of conjugate gradients, the same thing keeps happening, which is anytime you have an e to the minus 1, we put an e to the minus t next to it, and anytime we have an e to the minus t, put an e to the minus 1 next to it, and in the end, when the smoke clears, we get an algorithm that is completely written in terms of p. Right? So what did we show? We showed that, yeah, okay, so if we assume that our preconditioner is symmetric, positive, definite, then even if we don't know his Cholesky factorization, in fact, we can still pretend like we did and run the same iterations of CG. Yeah? And what is the catch? Well, the catch is rather than getting this YK that solves that system that we wrote down a few slides ago, yeah? Instead, we get E times that. That's exactly what we wanted. That's going to converge to the solution of our system. Yeah? So in fact, now this entire algorithm is a version of preconditioned conjugate gradients with a preconditioner P. And the assumption is that P is symmetric and positive definite, but we don't have to compute his Cholesky factorization. And somehow this is fair, right? Because we decided that remember that if a matrix is SPD, then his inverse is also SPD. Yeah? So remember, when we're doing CG, we're trying to solve AX equals B, so somehow it's sort of reasonable for our preconditioner, which looks like A inverse, to also be symmetric, positive, definite, and we'll see a few examples of what those might look like. Okay, and here they are. So coming up with a preconditioner is largely an engineering problem, and the reason that I say that is that different preconditioners are effective for different problem domains. So in general, if you're trying to use one of these iterative solvers, you really need to look at your matrix and try and see if there's some structure you can take advantage of. But that said, there are a couple sort of common tricks that people try. There are a few eigenvalue bounds that can be used to try and say what happens to your condition number when you pre-multiply by one of these guys, but in general, you don't get so lucky. So my general advice to you is A, never run conjugate gradients without preconditioning, because preconditioners are very easy, at least the first one here. And B, try a few and just see which one works the best for you. And I would say that even fairly advanced numerical analysts would tell you the same thing. So let's see a few. So the first preconditioner is definitely the most easy to deal with, and that's just a diagonal matrix. Right? So what am I going to do? Well, in reality, gosh, I keep putting my eraser down. My matrix A has some shape, right? You know, A has a bunch of numbers like this. And in fact, what I'm going to do is just ignore all the numbers that aren't along the diagonal and then just invert the thing along the diagonal. Right? And at the very least, what that does is if, like, for example, the second row is 10 times the first row, and the third row is 100 times the first row or something, which happens sometimes, then that'll take care of these different scaling factors. Right? And remember that what we really don't like in conjugate gradients are eigenvalues that are very different, and what tends to cause that are when rows are very different scale. Which kind of makes sense, right? Because then sort of you're scaling one dimension a lot more than another. Yeah? Another idea, which is probably, which is very appealing given discussions that we've had in previous lectures, is to do something called a sparse approximate inverse. Where in fact, well, we only kind of know how to do one thing in CS205, which is solve least squares. And even though we are solving least squares when we do conjugate gradients, we're going to try and solve a smaller least squares problem as a preconditioner. So in particular, one thing you could do would be to write down some set of possible preconditioners, and then among those, minimize AP minus the identity matrix, the Frobenius norm. And what I mean here is that, for example, maybe what I do is I say, okay, I notice that A has a particular sparsity pattern, like he has a non-zero here, a non-zero there, maybe non-zero here, and